Math 3 Lesson Summary Video, Rational Thinking. This lesson is a solidify understanding task, which takes concepts developed previously and helps you formalize those ideas. The purpose of this lesson is to discover the relationship between the degree of the numerator and denominator of a rational function and its horizontal asymptote. A rational number is a ratio of integers, numbers. A rational function is a ratio of polynomials. If you remember from Math 2, we learned a polynomial is just a representative of a number. And so we can do all of the operations and things that we do with integers and numbers. We can do those with polynomials as well. We also learned that during the polynomial unit that each polynomial has a degree. So don't forget how to find degree. So the degree of the numerator is 0 here because there is no variable. The degree of the denominator is 1 because there's one variable, there's one root. It's to the first power. There's only going to be one real or imaginary or whatever root. When we look at the next one, we have x to the first power, x to the first power. So both of these have a degree of 1. Here's another degree of 1, but down here we have this cubic polynomial, so it has a degree of 3. Up top, it's a quadratic, and so it has a degree of 2. Down at the bottom, they're purposely trying to trick you because you see x to the first, but this is just a quadratic that's been factored. It's still quadratic. I've got x times x, that's going to be x squared. So it has a degree of 2 as well. So you do need to dig deep and go back and remember how to find the degree of a polynomial so that we can do this lesson. The next 2 pages of the lesson is actually something that you just need to work through. It wants you to use technology. I would use Desmos. You can use a graphing calculator, any kind of graphing device. To graph these functions and then identify all of this information about the graph. So using the equation, identify what is the degree of the numerator, what is the degree of the denominator, and then using your graphing technology, what is the horizontal asymptote, what is the vertical asymptote, and where are the x and y intercepts. And you want to do that for all 8 of these, well, 6 of these problems. The last 2 want you to just create and write your own and get some information about it just to see if we're looking for patterns. Remember, math is a lot of looking for patterns in things so that we can figure out what those patterns are and use those patterns to help us in the future. So go through and find all of this information about all of these graphs using some kind of technology tool. After you have found all of that information using your technology tools, we want to start looking for those patterns and looking for those relationships with each other. So things that hopefully we noticed. Back on the first page of the task, there was a blank chart, and that is what we wanted to use to summarize and find all of our patterns in all of those graphs. So if you go back to that, notice that what we're looking for is where is the degree of the numerator less than the degree of the denominator, and where is the degree of the numerator equal to the degree of the denominator. So if I look through at least the 6 that were given to us, not the ones that I made up, and look at which numbers were the ones that had the degree of the numerator was less than the degree of the denominator, that would have been number 2, number 3, and number 5. Of the 6, where was the numerator's degree equal would have been number 1, number 4, and number 6. And so we want to look at those particular graphs and find things that we found were in common, things that were different. Were they really different, or were they just unique to each graph? And one of the first things that becomes very noticeable is that all of the graphs where the degree of the numerator was equal to the degree of the denominator, their horizontal asymptote was 0. And in fact, none of the ones where their degrees were equal to 0. Only the ones where the degree of the numerator was less than the degree of the denominator had a horizontal asymptote at 0. And that's one of the big takeaways that we want to get from today. This is because if we think about taking powers of numbers, if the degree of the numerator is less than, that means I'm taking x to like the second power and x to the fifth power on the bottom. If you're taking the same number to a larger power, that's always going to make a much, much, much larger number. And when you take a number and divide it by a much, much, much larger number, it tends to get closer and closer and closer to 0. And so that's why we end up with that horizontal asymptote. As x is getting bigger and bigger and bigger and bigger and bigger, that denominator is going to be getting much, much bigger than the numerator. And so we're getting closer and closer to being nothing because we're taking something small and we're dividing it by something big. And so that is why we end up with a horizontal asymptote that is equal to 0. What we notice about 1, 4, and 6 is that they all have a horizontal asymptote that is not 0. It's some other number. So how did it turn out to be some other number? And what is that other number? And that's where we had to start looking for some patterns. So one of the things that we started noticing was that if you just looked at the leading coefficients, so there's some vocabulary, leading coefficients of the polynomial on the top in the numerator and the polynomial on the bottom in the denominator. What it looked like was that the horizontal asymptote always ended up being at whatever the leading coefficient was in the numerator divided by whatever the leading coefficient was in the denominator. And this also makes sense. If our degree on the top is the same as the degree on the bottom, as x is getting bigger and bigger and bigger and bigger, we're taking x to the same power. And so it's just constantly going to be the same number. All the other x's are going to be so small in comparison to that largest exponent and that largest power. And so that means that they really end up being the same thing. The only difference is if that x to a power happens to get multiplied by a number. That's the only real distinguishing characteristic. And so that's why only the largest exponent matters and why it's the leading coefficients that end up being what we're getting closer to, because everything else is just kind of negated by the fact that these numbers are getting so big. And so we always end up with our horizontal asymptote being equal to the ratio of the leading coefficients. Now, finding all of the other pieces actually seem to have a lot of similarities that didn't really depend on the degree at all. For example, finding vertical asymptotes. Well, we happen to know that the only reason they exist is because we can't divide by 0. So if I want to find a vertical asymptote, I need to figure out where is the denominator equal to 0. So for both of these, if you set the denominator equal to 0 and solve for x, that's going to be how we find the vertical asymptote. And we did notice that sometimes we can have more than one vertical asymptote. So to find the vertical asymptote, it was always where the denominator ended up being equal to 0, because we can't let that happen. Anything that would make the denominator equal to 0, we have to put a fence up and not let that happen, because we don't want to divide by 0. When we're looking for intercepts, don't forget we have two types of intercepts. We have x-intercepts and we have y-intercepts. And we had already talked about with the parent function and the key features said that we didn't have any. Well, that's true if your asymptotes are on the x-axis and the y-axis, because if you have an asymptote on those axes, they're never going to touch there. But we also know we can shift them around and transform them. And so sometimes we do end up with x-intercepts and y-intercepts. And so we needed to notice in the patterns, what was it that was giving that away? What was giving us an x-intercept or a y-intercept? And we did notice that it was pretty much the same for both of them. The x-intercepts ended up being the roots or the zeros of the polynomial in the numerator. So the numerator's polynomial, wherever it's equal to 0, is where the x-intercepts ended up being. And that makes sense, because if I'm going to have a fraction, the only way I can get 0 from a fraction is if the top number of the fraction is 0. I can't divide by 0. And if I take any number and divide it by something else, it's never going to be equal to 0. The only way we can get 0 is if the top number is equal to 0. So whatever that numerator polynomial is, wherever it is equal to 0, that's going to be how I get a x-intercept that happens to be equal to 0. Now, to find the y-intercept, this is no different than every other function we have ever studied. If you remember when looking for key features, to find the y-intercept is the point where x is equal to 0. So in order to find a y-intercept, we just have to substitute 0 in for x and figure out what y is. So that's going to be the same. There's nothing that has changed there. So substitute 0 in for x and find what is the y value that we get when we substitute 0 in for x. And that's the same for all functions. That's just the behavior of function.